Okay, good morning. Can you hear me?
Good morning, sir.
Good morning, sir.
Today we are going to start a very important lecture for you. That is we call shear force and bending moment diagram. So this topic is really very important for your engineering life. If you do not understand shear force and bending moment diagram, I can give you guarantee that in upcoming courses you will suffer a lot for this shear force and bending moment diagram. Okay, can you see the presentation?
Yes, sir.
Like in this particular course, we will be doing some hand calculations of finding the shear force and bending moment diagram for simply supported structures or cantilever structures. That is we call the determinate only. So in determinate one, you will understand in the structural analysis one course. Okay, how to draw the shear force and bending moment diagram. Okay, so let's start on with this topic. Shear force and bending moment, particularly for beam. What is a beam?
The below the
The
slab,
beam
the
is a horizontal
horizontal.
structure that carries the load of the above structure like floor and transfer it to the column, and then the column transfer it to the ground.
Okay, so you're supposed to know from maybe
Load bearing
the
structure.
drawing course. So, okay, by the way, we can study here. A beam is a bar subjected to force or couples. So, do you know what is couples? So, couples is also force. Okay, if there are two forces acting oppositely and produce the same moment. If these two forces are same, this is P force and this is also P force. Okay, that means the same amount of force, the distance is L. So if you take moment at this point A, the moment is P into L. If you take moment at point B, the moment is also P into L, but it rotates. Okay, so this kind of force action we call the coupled forces. So a beam is a bar subject to force or couples that lie in a plane contain the longitudinal of the bar. So it usually lie on the longitudinal directions of the bar. Okay, sorry, the load actually. This is the, if you consider this is a beam. Okay, if it is a beam and the loads you can see are perpendicular with respect to the line of longitudinal bar. Okay, so according to the determinacy, a beam may be determinate or indeterminate. Now you should answer me from the basic mechanics basic, what is determinate and what is indeterminate in terms of equilibrium conditions.
So when three equations are known, like summation of moment, summation of horizontal force, and vertical force are zero, then we can call that
So these
beam
three
as
equations are
indeterminate.
known. But if a beam, if we have
Yes, sir.
three equations maximum, three unknown maximums, so that time you can say this is a determinate. So statistically determinate beams are those beams in which the reactions of the supports may be determined by use of the equation of static equilibrium, right? So you know what is the equation of static equilibrium: summation of f of x, summation of f of y, summation of moment. These three equations you have. By using these three equations, if you can determine the unknown of a beam, so that means you will call it determinate. Suppose here you can see there will be a vertical reactions, there will be a horizontal reactions, and there will be a moment. So three unknowns are here due to the fixed support, right? So
Yes, sir. Fixed support.
you have three known equations. So by using these three known equations, three unknown equations can be found. So that can be determinate. Here you can see this is a pin support. So pin support will have the two reactions, vertical and horizontal, and roller support will have only the vertical reactions. So 1,
Vertical
2,
reaction.
3. So three unknowns. So that means it can be found. Do you understand? Okay, similar
Yes, sir.
situation for this. Now if I say a beam is having the fixed support, and here it is having the roller support. So due to the roller support there will be one reactions, right? And due to the fixed support there will be how much? How many reactions? Sorry,
3,
3.
sir. 3.
3 reactions.
3.
So 3 plus 1, 4 unknowns. So that time we cannot
Yes,
say
sir.
this is a determinate. We can say this is a indeterminate beam. So this is the
Indeterminate
situation
beam.
here. So statistically indeterminate beams, if the number of reactions exerted upon a beam exceeds the number of equations in static equilibrium. So that means if more than 3, the beam is said to be statistically indeterminate. In order to solve the reactions of the beam, the statistic equation must be supplemented by equations based upon the elastic deformations of the beam. So these are some process they are discussing. So the degree of indeterminacy is taken as the difference between the number of reactions of the number of equations in static equilibrium that can be applied. So that is sometimes we call degree of indeterminacy. Okay, that how much reactions or how many unknowns we have that we cannot find. So if you consider this one, there is 4. So you can say 4 minus known equation is 3. So for this one, degree of indeterminacy is 1. You understand that? So this is your degree of indeterminacy. That means one reactions you cannot determine. So that's why this beam become indeterminate. Okay.
Sir, please repeat again, sir. I don't understand, sir.
So there are four reactions. There are 4 unknowns, and you have 3 equilibrium conditions. So if you reduce this unknown minus the reactions, known reactions, so it is 1. So that means what? 1 reactions is indeterminate. Okay. So that's why they call the degree of indeterminacy is taken as the difference between the number of reactions to the number of equations in a static equilibrium that can be applied. So here you can see that for this one, who wants to join now? Okay, for this one, as I said, there are 3 reactions, right? Okay.
Yes, sir. Fixed support.
Okay, fixed support. If you consider, okay, this way. So 3 minus what?
3 minus 1.
No, sorry, 4 minus 3.
4 minus 3.
So for this
3.
one, it will be 1 degree of indeterminacy. Okay.
Sir, 4 minus 1 is like this, sir. They have connection T1 and R1 of this loop, sir.
No,
I'm not
no.
clear, sir, about this.
We are talking about indeterminacy. We are talking about indeterminacy. So that means one equation is unknown here. If you find this kind of, do you understand? Or in other way, you can say like this. How? In case of the propped beam shown in the, there are 3 reactions, R1, R2 and M. R1, R2 and M. So only 2 equations, summation of M naught and summation of FB can be applied. So since there is no X, okay, no horizontal forces, so summation of FH is missing here. Okay, so that's why you have available 2 equations, unknown are 3. So unknown 3, available equations 2. So it's become 1. Do you understand? So degree of indeterminacy also 1. You can also use this technique, simple technique. So we know fixed support will have 3 reactions and roller support will have 1 reaction. So total reaction is 4 and we have equilibrium conditions 3. So we reduce 3. So it is also 1. So you can go either in the book format or whatever I explained. Both are same. Do you understand? What I explained, this is the base format. Is that clear now?
Then apply.
Okay, so then we can move to the types of loading. So we know all we have the point load if it is a beam. So this kind of loads we call the point load if it is concentrated on a particular point. Okay, so type of loading. So first of all we'll have like point loading, then we have the uniformly distributed load, or sometimes we call UDL. UDL, maybe in basic mechanics you deal with this kind of load, right? Uniformly distributed load, and we call it
Yes, sir.
UVL. UVL, uniformly varying load. So the variation of the load is uniform with respect to the length.
Yes.
And we call it applied couple. We call it applied couple. How we consider this applied couple? So this is very interesting. Suppose if we have another member here, and this member is having, suppose P force here and another P force here, and this is suppose L. So if you take moment in this point, okay, if you take a free body diagram, you might get the moment M equals to what? P into L. Do you understand?
Yes, sir.
Yes, sir.
So instead of writing this member, so we may apply this kind of moment directly. So that is sometimes we call the applied couple. The mechanics is very interesting if you know. Okay.
Sir, what is UDL, sir?
Uniformly distributed load. Okay. And UVL is uniformly varying load. That's clear?
Yes, sir.
Yes, sir.
So you know right now types of supports and number of reactions for each type of supports, and you know the loading conditions. So now we are good to go for the shear force and bending moment diagram. Okay. So before going to that, we need to discuss about the sign convention of shear and bending moment diagram. Okay, suppose we have a beam. This is a simply supported beam. Okay, in a certain locations, we want to know the moment and shear. So here you can see, consider a simple beam shown of length L, and that carries a uniformly load, we can see, throughout its length, and is held in equilibrium by reactions R1 and R2. So here we can see basically three unknowns, but particularly we need to calculate R1 and R2. So we have available three equations, so we can easily find out this. So assume that the beam is cut at a point distance x. So at this distance x we want to cut this beam, suppose you assume. So from the left support and the portion of the beam to the right of C was removed. Removed. So if you take a section and you remove this portion, so there you will get this kind of section, right? So we know if we take a section, the free body diagram, so here you will get a shear force. So they are considering the downward shear force and anti-clockwise moment, right? If you take a section,
Yes, sir.
if you take a section, right, so what are the things you should have? If you remove these one, okay, if you consider these one, okay, so here you will have unknown reactions vertically, horizontally, and moment. So you have shear force, you have axial force, maybe P, and you have moment M. So usually you have these three unknowns if you take a section. But now question is that in these sections you have only two forces, shear force V and moment M. Why axial force is missing? Who can answer this?
Sir, axial force will be 0.
Yes, exactly. Axial force equals to 0. But can you tell me why axial force, internal axial force would be 0?
Sir, angle is 0, sir.
No, this is not about the angle. Can you try? Do you want to try?
Sir, is it because the load is...
Because?
Sir, I was just asking that is it because the load is coming from vertical?
Sir,
the beam is facing vertical load on that point.
Very close. The point is that these are the internal forces, right? You apply this load, that's why shear force develop. But you did not apply any axial force. Did you apply any axial force?
Yes, sir. That is... No, sir.
You did not apply any axial force. So how come the internal axial force will develop? Do you understand? So that's why this force is 0. Because no external load applied as a what? Axial load. So that's why internal axial load also 0. Do you understand? Otherwise, you must have 3 unknowns. But now you have 2 unknowns because only vertical and moment are there. So we need to calculate this V and M. Do you understand? So here you can see that we yet don't know about the R. So we need to calculate V and M. So from these structures, if you take the summation of vertical, you have 2 unknown, R1 and R2, right?
Yes, sir.
Are you getting the concept? You need to go back to the little bit of basic mechanics. How to calculate the reactions? How do you calculate the reactions? If two reactions are unknown, usually if you take first summation of vertical, first, it will not work, right? Because 2 unknowns are there. But if you take moment at point B, so if you consider clockwise,
we will get R1.
So that means R2 will be 0 that time. You can calculate the R1. So once you know the R1, you can calculate the R2. So this is a simple technique from basic mechanics, right?
Yes, sir.
Okay. So once you get the R1, you can calculate the R2. So once you know the R1 and R2, can you calculate this V and M? Because this V is unknown and this M is unknown. But this R is known. Do you understand or not?
Sir, maybe V we can calculate by taking summation of vertical loads.
Exactly. If you take summation of vertical load, you can see R is known, right? And V is unknown. And Wx is known, given value, right?
Yes, sir.
So unknown can be calculated by summation of horizontal force, vertical forces. Okay. So if you consider vertical, upward positive, so that time you can get the value of B. So again, if you take moment at point C, right, you can calculate the value of M. Or if you wish to, okay, I think it is better. If you take moment at point C, you will get these forces 0 with moment. So you will get the R1 is developing some and this is developing some, and moment. So that time you can get the value of moment. So again, I should say this is a part of mechanics, that is the basic mechanics. So that's why I have given you one assignments from the basic mechanics. Do you understand the importance of that assignment now? Okay. So sign convention, here you can see, just keep in mind or look into this very carefully. Suppose you have a beam. You have a beam, maybe it is simply supported. Okay. Okay, you have a beam. So you have taken a section of this beam. Okay. So if you take the section, you have two parts, right? Part 1 and part 2.
Yes, sir.
So if you draw a free body diagram, so part 1 will be look like that. This is the reactions R, right? Maybe R1. So part 1 will look like R1, and here you can see you will get
Shear
downward
force.
shear force and bending
Moment.
moment like this. Okay. So this is the scenario for portion 1. And if you draw the scenario for portion 2,
R2, sir.
okay, forget about this horizontal reaction right now, because in this part we don't have to deal with that much. Forget about this is horizontal. Now consider this is R2. So here you can see for this segment 2, so this is V and this is M, right? So this,
Yes, sir.
This is segment 2 and this is segment 1, right? So from the equilibrium conditions, we know whatever the value of B, this one, it should be equal and opposite of this one, right?
Okay, sir.
That time if you add these two, V value, it will 0. It will make what? 0.
Yes, sir.
If it is minus 10, this should be plus 10.
Plus 10.
If we add these two, it should be 0. That means what? The situation is in equilibrium condition,
Sir.
right? The member is in equilibrium condition. Is that clear?
Yes,
Yes,
sir.
sir.
Similarly, if you find that counterclockwise or anti-clockwise movement, right here, it's 100. Just for an example, I don't know. I assume, right? It should be 100. This is clockwise. So for anti-clockwise, if you consider the minus 100, for clockwise plus, it will be like this. So what does it mean? Summation of all the forces on a section must be 0, right? Summation of all the forces on a section must
Yes,
be
sir.
0.
If the section is in equilibrium.
No, must be 0, then you can consider this is an equilibrium condition.
Yes, sir.
If it is not, that is not in equilibrium, so it becomes the indeterminate. It has some redundancy. Okay, so this is the scenario, right? First of all, do you understand that one, that case? Hello? Hello?
Yes, sir.
Do you
Yes, sir.
understand this one?
Yes, sir.
Okay. So I'm not supposed to discuss these details in this class because you're supposed to know this from the last prerequisite course. But just to give you a revision. Okay. So now here
Okay,
you
sir.
can see that this is a section, right? This is a segment. For this segment, this is the right part, right? This is the left part, right? Right end. And this is the left end. Hello?
Yes, sir.
For this segment,
Yes.
this is the left end and this is the right end, right?
Yes, sir.
So if you find a section and if you find the section is on the right side of the portion, right? Portion 1. So portion 1's right side is this, right? So if right side is having downward shear and anti-clockwise movement, so that one we consider the positive sign. And similarly, if you find a portion and left portion, if the shear force is upward and clockwise, right? If it is clockwise, that time we also call the sign is positive. Is it giving you more complexity or confusion? You understand these or
No,
not?
it's clear, sir.
No, sir. Understand, sir.
Okay. So if you find a sectional view, if you consider the portion 1, so for the portions, if you consider the right side, so for the right side, if you find the shear is downward and movement is anti-clockwise, that means this shear is positive and anti-clockwise movement is positive. That is the things we consider. And for the
Yes,
segment, if you start from the left side, upward shear is positive and clockwise movement is positive. So suppose if I say this is a separate beam. Okay. So now if you find this beam from the left side, this is the left side of the beam, right? And this is the
Yes, sir.
right side. Very good. So now we will consider from the left side upward is positive shear.
Positive.
From the
Positive.
right
Yes,
side downward is positive shear. So for this case we
Positive.
consider this is a positive shear. So how do you look like it if you consider the center point section? So have a look. If you push this one upward, it will be look like this. And if you push it downward, it will be look like this. So this is your positive shear. Can you get the matching of this?
Yes, sir.
Yes, sir.
So what does it mean? For a segment, left side upward is positive shear, right side downward shear is a positive shear. Is it clear now?
Sure. Yes, sir.
Yes, sir. Clear, sir.
Yes, sir. Clear.
Okay, very good. You guys are very good student. Okay, now come to the moment. Okay, so can I erase this? Okay, let me explain
Yes, sir.
moment here.
Yes, sir.
Yes, sir.
Okay, if I can erase, I can erase. Okay, so now come to the again a section or a portion of beam. Just so excuse my drawing because I'm using my mouse instead of mouse pen. So it's difficult to make the line straight, by the way. So if it is a beam, so this is your left portion and this is your right portions. So according to the norm, we can see that for the left portion, clockwise is positive, right? Do you understand?
Yes, sir.
Yes, sir.
Upward
Clockwise is
shear
positive.
positive.
And for the right portion,
Share up.
Anti-clockwise.
anti-clockwise is positive. So do you have pen with you? Can you hold a pen right now?
Yes, sir.
Yes, sir.
Okay, so hold the pen in horizontal directions and use your left thumb as a left end. Use your right thumb finger on the right side of the pen after laying it in horizontal direction. Okay, did you hold it?
Yes, sir.
Yes, sir.
Okay, now press downward. Now press downward the pen. So it should be look like that. Are you getting this kind of
Yes,
shape?
sir.
Yes,
Sir.
sir.
Okay, so what does it mean? What you are doing now? You are pushing or you are
Positive
giving the
bending.
movement like this way in the left hand and giving this direction in the right side, right? So if you apply this kind of positive movement, positive sign movement, not positive movement, positive sign movement in the both side, you will get this kind of direction. So that time we call it the positive bending. Okay, do you understand that?
Okay, sir.
So what does it mean?
Yes, sir.
In case of left hand, the clockwise movement is positive. In case of right hand, anti-clockwise movement is positive. Okay.
Yes, sir.
Okay,
So
sir.
as similar, the opposites would be the what? Negative. So just consider a member. So in the left hand, if you consider the anti-clockwise movement,
Anti-clockwise.
and the right hand if you consider
Right
the
side clockwise.
clockwise movement, just change your thumb up to down before you apply the load on the top of the pen, right? Top plane. Now you just apply the load on the bottom of the pen,
Bottom.
right? So can you see the thumb directions and the bending of the pen? It should be look like this, right?
Yes, sir.
Yes, sir.
Right? Okay. So if you find left hand is having anti-clockwise, so that time we consider this the negative moment in case of drawing SFD and BMD actually. And if you find the right side is the clockwise, that time we also consider the negative moment. So should not be confused, sir. In the right side we started and clockwise, why do you consider the negative? You understand now? Why anti-clockwise
Yes, sir.
we
Clear.
consider the positive? Because the drawing you can start from the left hand side or right hand side. Either way you can start the drawing of SFD and BMD, shear force diagram and bending moment diagram. Okay, the real challenge, you can start any directions. So if you start from the left end, you consider the clockwise movement and upward shear is a positive. If you start from the right hand side, anti-clockwise movement and downward shear would be the positive. So similarly, if this is the positive shear directions, right? So it would be the negative. So what will be the negative? The left hand downward
Left hand will be downward shear.
and right hand
Right hand will be upward shear.
upward shear. Clear?
Yes, sir.
Okay. So
Yes, sir.
to remember this one, positive bending and negative bending, you can use one mnemonic like that. If you find the boot is in a proper condition, suppose this is your boot, right? So that means you okay, this is positive, right? Slip down, what? You are not in a good conditions, negative mood. You can use this mnemonic to remember. I hope it's easy to remember, right?
Okay, sir.
Okay. So now if I erase these whole discussions from these slides, you can see that you guys are expert now on this slide. So you can see, sir, okay, what you want to mean by positive bending by this curve and negative bending by this curve we understand. Are not you?
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
Okay, so you see, you guys become expert. Okay, so let's discuss about the relationship between the force, shear force, and the moment. Okay, so this is the applied force. Then we will try to develop the shear force issue due to the application of forces on the member and the bending moment. Suppose you have a member which is simply supported and you have some sort of random loading actions. And from this one, if you consider a small sections, like after x distance, we consider a segment, okay, let me change the color, C and C prime. Can you see C and C prime section, which is very small? Can you see this? Dx. The distance
Yes,
is
sir.
very small. So along with this, you will have this kind of loading also, right? So if you magnify this section, right, if you take this section out, right, so this is your left portion and this is your right portion of the portion, right? So as we just discussed the sign convention, we know in the left side clockwise movement and upward shear
And
force,
upward.
in the right side anti-clockwise movement and downward shear force. Okay, and in the top we have load from this portion to this portion. We can see this, and this load looks like uniformly distributed load, though it is not uniformly distributed load in the actual scenario, but since this is a very small portion, the curvature conditions we can remove. Okay, we can neglect. So it looks like a uniformly distributed load, so that means this load height is W and this distance is dx, right? You understand?
Yes, sir.
Yes, sir.
So if you consider this height difference is very small, if you consider this height difference is very small, so that time we can consider it's almost rectangular, right?
Yes, sir.
So that time we can say load equals to W into del X. Do you understand how did they consider W into del X?
Yes, sir.
Okay.
No, sir.
Okay.
They converted the UDL to concentrated load.
No, this is the load exactly
So
passing
by
through the
multiplying
center.
the distance.
This is the total amount of load. Okay, so we know for a particular what is called section, the load passed through the center or CG point. Do you understand?
Yes, sir.
So if you have the loading scenario, if it is a uniformly distributed load, so all the load passes through the center. So you need to consider the total amount of load. So if this is W and this is L, so that means this total amount of load is W into L. So this is the situation. Okay.
Yes, sir.
Okay. So now if you take the summation of vertical actions, here you can see V is acting upward, right, positive, and this V plus dV, why they consider dV, oh sorry, not dV, del V, because they assume that since shear force will be little bit of increase here, so they are assuming that with respect to del x distance, the shear force will increase a bit. So that's why they consider the shear force on the C prime locations is V plus del V. Do you understand that one?
No, sir. Why it was increased, sir?
Sir, is it just an assumption or it will
You can
actually
see
increase?
the load is increasing here. Right? Hello? From the section
sir.
C
Yes,
and
sir.
C prime. So little bit of increment on the C prime. So that's why internal force will also increase.
Yes, sir.
So they don't know how much it will increase. It's a small segment they consider, which is del V. Okay. So similar situation for the moment also. M plus del M. So now if you take the vertical, summation of vertical, so you can see V is acting upward, so it is plus, and this V is acting downward, so this is minus, and this W into del X is acting downward, so this is minus. So if you take the summation of these, you find that V equals to V plus del V. So here if you take the summation of these V and these V will cancel, sorry. These V and these V can be cancelled. So here you can see that del V and W del X are here. So you can say that del V equals to minus Wx this way, right? So if we
Yes, sir.
consider del Vy del X, so which can be write like this, dV by dx, which is equals to minus W. So what does it mean? If you do the differentiation, right? Sorry, if you do the differentiation of shear force, you will get this W. So this is the mathematical scenario. Do you understand this or not? If you do the differentiation of V, you will get the W, which is opposite in directions. So this proves that if you do the integration of load, because we know differentiation and the integrations are opposite, right? Hello?
Yes, sir.
Yes, sir.
So if you do the integration of load, you might get the V. Do you understand that?
Yes, sir.
Yes, sir.
So if theory says that differentiation of the shear, we can get the load. So integration of load can give us the shear. So what does it mean? If you take the area of a load, you can get the shear value. This is the simple technique. Okay. Do you get the technique? Because this technique we'll use for the drawing SFD and BMD. So in simple way, we can say that if we take the area of load, we'll get the shear. Okay. In reverse, we can consider if we do the derivation of shear. So if we do the differentiation of shear, we'll get the load. Do you understand? This is a part of calculus. Is that clear to you or not? Hello, are you getting my voice?
Sir, if we take the area of the load, we will get shear force, right, sir?
It's the mathematics is showing like that. This is
Yes,
not
sir.
my statement. The proofs is like that. If you take the area of this load, you get the shear. Integration of load means what? Okay. So similarly, if you take the moment at C point, where? At C point, right? This is the C point. So within this equation, we will try to develop one relationship between the moment and the shear. So now what is the moment we have? This will be 0, right? Because it's passing through the C point. So
Yes,
this
sir.
force will not generate any moment. So this is M
Moment.
clockwise plus we consider, but here they consider anti-clockwise is plus. It's up to you. Okay. While you take the summation of MC or moment, if you consider clockwise as a plus, so all the clockwise movement you will write plus, or if you consider anti-clockwise as a plus, it's up to you. This is only for summation of moment you can consider. So they consider anti-clockwise is plus. Do you understand? You can consider clockwise is plus, so that time anti-clockwise will be minus for you. So we can do by considering the clockwise plus also by changing the sign. Here we can see. So if you consider all the clockwise is plus, so that means anti-clockwise will be minus. So M into dm. So this is anti-clockwise. So this should be minus, right? Anti-clockwise with respect to C. Hello?
Yes, sir. It will be minus.
Yes, sir. Anti-clockwise.
Okay. So do you know how does it consider clockwise or anti-clockwise? With respect to C, you can find that this rotation is anti-clockwise, right? But with
Yes, sir.
respect to C, this rotation is, this M is rotating clockwise.
Clockwise.
So that's why we consider plus, just for an example. And now come to this force, V into dV, because this force will be 0, right? Hello?
Yes, sir.
Where did they take the section? I think
Sir, why
they
it is 0?
just a moment. Why it's 0? Because it's passing through the center. Just a moment. I think they consider the section at point C prime. Yes, they consider the moment at point C prime. Okay. So if you consider the moment at point C prime here, okay, this is C prime. So this is 0. Sorry, this is clockwise plus, this is anti-clockwise minus. Okay, so now come to this one. So this V here will be 0, but this V into, sorry, this V plus del V will produce 0 moment. Now you should ask why it is 0, because this V plus del V passing through the point which is C point. So there is no moment arm. What is moment? P into L.
Force into distance.
Right? So if L is 0, so your moment will be 0. So now do you understand why V plus del V equals to 0?
Yes, sir.
Okay. So here we have two forces, which you can see that V is rotating with respect to this C prime clockwise, right? V. So that's why we'll clockwise plus, as we consider clockwise is plus. Okay. So what is the distance? What is the distance? V into del x.
Del x.
Okay. So V into del x. This is the moment. Now we have another moment, which is, this is the load, and since we consider this is equivalent to a rectangular, right? This is equivalent to a rectangular. So for the rectangular, what is the distance of CG? half.
Del by 2.
So del x by 2. So what is the load? Load is W del x and distance del x by
Del x by
2.
2.
Can you find this one? So, but this should be minus. As we consider clockwise is positive. Why it is minus? Because here you can see with respect to C, it is C prime, it is rotating anti-clockwise. So there is a thumb finger rule to find out the clockwise and anti-clockwise rotation. So which point you are calculating the moment, you try to put your thumb finger there. Okay, if you put either any hand, you can put it. So and then you try to force according to the direction of the force. So you can see, if you put the force of B, it is rotating clockwise. If you put the force of omega del x, sorry, W del x, whatever you like to say, it is rotating anti-clockwise, right?
Yes, sir.
So you can see right now. So even though if you consider the clockwise is positive, if you do the simplification of it, you will find these the same things, right?
Sir, can you repeat again, sir? Del x by 2, sir.
Okay. So if it is a rectangular area, what is your CG distance? If it is L, the distance of CG would be L by 2. So this distance is del x. Sorry, yes, del x here. So CG distance would be del x by 2.
Yes, sir.
Okay. Okay. So now here you can see that we find the equations del m equals to v del x minus this and this. So we know del x is a small portion. The length of del x is what? Very small. So less than 1. If you do the square or if you multiply with this fraction, it will be more smaller, right? Like if you multiply by 0.5 into 0.5, what does it mean? It produces more smaller value than 0.5.
Yes, sir.
It's getting the concept. Hello. Hello. Are you having Are you having internet
Yes, sir.
problem or it is okay? If you multiply by 0.5 into 0.5, so
0.25.
you get 0.25, right?
Yes, sir. The value will getting.
Yes, sir.
So the value will getting more smaller, right?
Yes, sir.
So as we consider that del x is a very small value and it is having the square value. So it will be more smaller. So smaller value multiplied with this term will be more smaller. So that's why we are going to ignore this term. We consider this is tends to 0. We consider this is tends to
Yes, sir.
0. So if you consider this one, we can see that we got this value, that is del m equals to v del x. So instead of this, we can consider this one, del m by del x equals to v. So what does it mean? If you do the differentiation of moment, we'll get the shear. You understand? If we do the differentiation of moment, we'll get the shear. In opposite way, can we say, if we do the integration of
Shear, then we will get
shear,
We will get the moment.
we can get the moment.
Yes, sir.
So what is the mathematical operation we can see here, that if you do the integration of shear, that means what? Area of shear might give us the value of moment.
Moment. Yes, sir.
So now if you make the relationship with this all, area of force will give us the shear. So what is our main target? Usually our main target is to draw shear force and bending moment diagram. So from this force diagram, if I consider FD, from the force diagram, we need to calculate the SFD, that is shear force diagram. Okay, then we need to calculate the BMD. Okay, so we know, if we know the force diagram, if we do the integration of this force diagram, we'll get the SFD, and once we know the SFD, we can get the BMD, right? Hello?
Sir, what, sir?
Yes, sir.
Yes, sir.
Sorry. I don't get your question. Can you repeat? Hello? Okay. So at least we have understand that if you do the integration of force, we can get the shear force, and if you do the integration of shear force, we can get the bending moment. In reverse condition, we can consider that if we do the differentiation of bending moment, we can get the shear force, and if you do the shear force differentiation, and we can get the force, applied force. Is that clear now? Hello?
Yes, sir.
Okay. Okay. So before going to the drawing of the diagram, you should consider some issue here, some common relationship. So we have loads. So in case of loading, we know we have point load. Sometimes we call this a constant load, or we call it UDL, right? And this is UVL. And now the question is that what is this zero, constant, and this linear? So this is the line. If you find the load are point load, that time you have 0 degree of line, that means no line, only the point load. If you find you have UDL on a beam, you will find the line is constant. If you find the load is linear, sorry, the load is UVL, that means the line is linear. You understand? So this one with respect to the line. So what is the situation? If you find the load is point load in the shear force diagram, you will find the line is constant and it is increasing gradually. If the load is point load, load diagram line would be 0, shear force diagram line would be constant, moment diagram line would be linear. Do you understand this one? This is actually the line of action. How will you draw the diagram? Might be confusing. Okay, let me explain the UDL. If you find the load is UDL, if you find the load is UDL, are you getting my voice?
Yes, sir. Yes, sir.
If you find the load is UDL, so in load action or load diagram, you will find the line is constant. Can you see the line? This is straight line, right?
Yes, sir.
It's a constant line. Okay. So in case of the shear force diagram, the line would be linear. This is the line. Okay. The line is linear. And in case of moment, it's going up actually gradually. In case of line of degree, it is look like parabolic. Okay. Now come to the UVL. If the load is UVL, so here you can see in the load diagram the line is linear, right? In shear force diagram you get the parabolic. Okay, you get the parabolic shape, and in case of moment you will get the cubic. Sorry. Is that clear or not? So there are another way, we call it, if point load is given in the support, so line of action or degree of line is 0 degree. For shear it would be first degree, and for moment it would be, oh sorry, I just messed up. In case of degree equation, okay, so if you consider the point load, so no line generated here, right? So no question about the line of action degree. But in case of shear it would be 0 degree line. I hope you know what is 0 degree line from the numerical analysis, which is a straight line, right?
Yes, right, sir.
In numerical analysis,
Yes,
I
sir.
hope you know the equations. So the line is 0 degree for shear, and in the moment it would be first degree. Okay. And in case of UDL,
Okay, sir.
have a look. The line started in 0 degree. So second would be the first degree. Second means what? After that we consider the shear force, and that would be the second degree. This is the according to the equations, line of actions, right? Degree. If you consider the
Yes, sir.
if you consider the UVL, have a look. You started with the first degree line. You started in the first degree line in the loading condition. In SFD, you will get the second degree, that is called the parabolic. In BMD, that is the bending moment diagram, you will get the third degree in the cubic format.
Sir, I have a question, sir.
Yes.
Sir, 0 degree or 1 degree, both are, sir, straight line, sir.
Don't you see the constant and the linear? So do you understand the constant and the linear increasing or decreasing?
Yes, sir.
So you can define. 0 degree is the constant, no increment. Indirectly,
Okay, sir, clear, sir.
there is no slope, guys.
Yes, sir.
Okay. So in case of linear, you get the inclined, right? Inclined one. So which is linear. Yet not started the curvature, right? Okay. So that means still you can define with the linear equations. Okay. So there are more situation for the line I will consider, like you should know that which curve is increasing curve, which curve is decreasing curve. Suppose have a look, the curve, this one is decreasing. Do you understand? this curve is decreasing. Hello?
Yes, sir.
Yes, sir.
This curve is decreasing. Is it right or wrong? If you consider this is the starting point.
Increasing.
Increasing, sir.
This curve is increasing. How do you define a curve is increasing or decreasing?
If it goes upward, it's
Depends on
increasing.
Compare with tangent, sir. Tangent line, sir.
Okay, you are very close. If you find the curvature, right? If you find the curvature is more, that time it is more. That is we call the increasing. If you find the curvature is getting less, so that time we consider decreasing. So have a look where you will get the slope higher. Here, right? Then gradually is going to be a straight line. So that means what? The curve is gradually decreasing its curve. Here you can see the perpendicular direction is almost zero.
Yes, sir. Now understand, sir.
Now understand. Okay, that's good. So similarly, this is also increasing. Sorry, decreasing. Right?
Yes, sir.
Okay. How about this if I say? Now this is increasing, right? If this is the starting point.
Increasing, sir.
This is also increasing. Right? Right? Sorry for my drawing, but here you can see. Okay. So this is also increasing. So it started from the flat line and gradually what is going on? Gradually it is increasing, right? Do you understand?
Yes, sir. Understand.
Okay. So in your book, just write this figure. I will discuss it later. This is for BMD. Now this is not the time to give you the lecture on this. I'll give you the answer later on this diagram. Okay, this is a shortcut technique to remember, but you are not on that level to give the lecture on this. But I will give you maybe after 2 or 3 examples. Okay.
Okay, sir.
Okay, just opposite is for SFD. Same curve, but opposite for SFD. Okay, just keep it. I'll discuss it later. Okay, so now the situation is that a curve can be can be decreasing like these directions, right? Can be decreasing like these directions. Do you understand?
Yes, sir.
Yes, sir.
Okay. And similarly, a curve can be increasing like these directions, okay, or it can be increasing like these directions. So when we'll select the increasing curve from this one, increasing, right? Increasing curve, and when we'll select the decreasing curve. Okay, decreasing. So each item we have two types. Like when we'll move to the parabolic situation or cubic situation, that time we must select the curve, right? Do you understand?
Yes, sir.
Yes, sir.
That time we must select the curve. So each category we have two types. So how do you select this? So these will help you to remember. Okay. Okay, this is
Okay, sir.
decreasing. Okay. I might take little bit extra time today. Okay. So now come to the drawing of shear force and bending moment diagram. So suppose you have a load of W. So forget about W. Consider W equals to 10.
W.
Okay. Okay, consider 100, no problem. Suppose 100 unit load is given in the middle of the beam. So suppose you consider L equals to 10 feet. Okay, L equals to 10 feet and W is maybe 100 pound. Clear? This is capital W.
Yes, sir.
Okay. So now we need to draw the SFD and BMD. So first of all, first step of drawing SFD and BMD is to calculate the unknown reactions. Find reactions. Find reactions. Okay? Do you understand that?
Yes, sir.
So I hope almost all of you know how to calculate the reactions. So how will you calculate this reaction RA and RB?
By taking moment, sir.
Okay, first of all, if you take moment at point B, okay, suppose clockwise is 0. Sorry, 0 and clockwise is positive, we consider. So that means what? If we consider RA into this 10, right?
10.
Which
Yes,
is
sir.
clockwise. RA into 10. And this load is acting downward and which is rotating anti-clockwise,
5.
right? Which
Yes,
is
sir.
rotating
Minus 100 into 5.
which is rotating anti-clockwise with respect to B, because we are taking moment at point B. So minus W into 5. Why 5? Because half of L by 2. So half of L by 2 equals to 0. Okay. So here you can see, you know the W. Only R is unknown. So RA should be 100 divided by L is how much? 10.
5.
Divided by 2 and divided
Yes, sir.
by
10.
10. Right? So RA should be 50. Right?
Yes, sir.
Yes, sir.
So if RA is 50, if you know RA is 50, what would be RB? You can simply take the summation of,
RB will also be 50.
you will simply take the summation of vertical. 0
Vertical force.
and vertical upward is positive. So for the first case, I'm just showing you the situation. I hope you guys can find out it. So RB also what?
50.
So this should be pound, as I said the pound. This should be pound, as I said pound. Okay. Now we can draw the SFD and BMD. So as I said that we can start from the right side or we can start from the left side to draw the SFD and BMD. Do you understand? Select the side.
Yes, sir.
Yes, sir.
You can select the side. You can start from the left or right. So if you start from the left, what is the sign? Upward and clockwise. Sorry. Upward and
Clockwise.
clockwise. Sorry. Right? These two are positive. If you find shear force is upward, you consider positive. If you find, oh, I wrote the sign opposite. Sorry. This is upward and clockwise. Okay. So if you find upward is the shear force and clockwise is the moment, we will consider these two are plus. So we consider neutral axis here. So for the plus value, we will go above of this line. For the negative value, we will come below. Okay.
Downward.
Okay. So as we said that we will start from the left side. So what is the upmost left side? A. So we'll start from A.
Yes, sir.
Okay. So at point A, we find there is a point load 50. Reaction is look like a point load, right?
Yes, sir.
Okay. So now look into the point load. So if load is point load, what is the situation in the shear force? Constant.
Constant.
So
Yes, sir.
it can be constant vertical, it can be constant horizontal, right? It can be vertical,
Yes, sir.
it can be
Yes, sir.
horizontal, both are constant, right? So here you can see that from 0 to 50 we have to go. First of all, if you consider the graph, this is a graph. Suppose I select the 50 value, which is 50, because I find this is upward positive. So that's why I select the 50 point on the graph. Do you understand? Now the question
Yes,
is
sir.
that which line will you use to connect these 2 points? So usually you have to use the constant line in the shear force. Do you understand
Oh,
that?
yes, sir.
So indirectly here there is no options instead of constant. Only option is constant line. Okay. So now where we are now? At point 50, which is positive shear. Clear up to this?
Clear, sir.
Yes, sir.
Okay. So after point A, we develop shear 50, and then we can see till the W, wherever you take the section on the beam, you will find the shear force is 50. You can take section at point X, you will get the
Yes,
V
sir.
equals to 50 plus 50. Do you understand? So that means what? Still we do not have any other force to disturb this shear force. So that's why we go constant up to the location of W. Do you understand? If you want to prove this, you can take any distance locations section. Suppose this section, you can prove it. How? Suppose this distance is X, right? And this is your 50. We know in the right hand side, this would be downward, right? You understand? This is V. So if you take
Yes, sir.
the summation of vertical, so what does it mean? This V equals to 50. Even just before W, if you take a section, still you will get this scenario, V equals to 50. That's why this force is constant. You understand?
Yes, sir.
Okay. But it gets disturbed when you just reach to the point of W. Why? Because in the point of W, we have something different, which is called 100-pound load. Right?
Yes.
So which directions is acting the load W?
Downward, sir.
So
What, sir?
downward. So if you start from the left side, upward is positive. So downward would be what?
Negative.
Very good. Downward would be negative. So here you have minus 100 downward, and you are on a location of plus 50, right? You are on a
Yes,
location
sir.
of plus 50. So if you add these two values, so you still have a balance minus 50.
Minus.
So what does it mean? In these locations, you should have the shear force here, minus 50. So you come from this point to this point, minus 50. So which line of action? Straight. That is we call the constant. Okay?
Yes, sir.
And now if you take a section here, anywhere, you will get the shear force is minus 50. You can take a section, no problem. From A to this section, you can take. You will get the shear force is minus 50. Do you understand? Hello?
Understand, sir.
Okay.
Yes, sir.
So until you reach the point B, there is no disturbance for this. So here till you be point B, you can continue. Okay. And after that, you can see this 50 is acting upward. So you have minus 50 and upward force is positive. Minus 50 and plus 50, which equals to 0.
Equal to 0. 0.
So keep in mind, for the determinate structures, you should end with the neutral axis.
Yes, sir.
So this zone is positive shear, this zone is negative shear. So for this particular beam, if you have this kind of point load, you can see 50% of the beam is facing the positive shear and 50% of the beam is facing the negative shear. Hello?
Yes, sir.
Yes, sir.
Okay.
Understand, sir.
That's very good if you understand.
Sir.
Okay, so now as we know that from the last basic that if you do the integration of load, we get the shear force. If you do the integration of shear force, we get the moment. So there is a simple technique, we can do
Yes,
the
sir.
integration of the shear force. So integration of shear force means what? We can take the simple area. So if you consider this is total is 10, there should be 5 feet and this should be 5 feet, right? So it looks like rectangle.
Yes, sir.
So 50 into 5,
Yes, sir.
how much?
250. 250.
So
Sir, 250.
it
Sir.
started from here and it ends here. So keep in mind, while you consider the area, you should consider the distance from the starting point to the end point, right? So this value is plus, so that means you have moment is also plus. So you have moment 250 is a plus moment. So as you consider moment plus means upward, above the neutral axis. So we select the 250 locations from the graph. Do you understand?
Yes, sir.
Now the question is that how do you join these 2 points? Which line of action will you apply? Now you can look back to the here. Have a look. If it is a point load, we started with which kind of load? Point load. We started with the point load. So no line of actions here, but in SFD 0 degree line. In BMD it would be first degree. So first degree is the linear line, right? Do you understand?
Yes, sir.
Okay. So as we can find the point, now the task is to connect these 2 points. So which line of action will follow? This first degree.
Linear.
Okay.
First degree linear.
Okay. So we can connect like this. Okay. So now here we are, which is plus 250. And after that we can see starting point is this and ending point is this. And in this range there is a shear force which is minus 50 into 5, which equals to
Yes, sir. Minus 250.
250. Okay. So what does it mean? This portion generates what? 250. So this is the starting point and this is the ending point. So balance should be always in the ending point. So this is the starting point and this is the ending point for this segment. So where did you put the balance? In the ending point, right? So similarly,
Yes, sir.
from this is the starting point for this segment, this is the ending point. So balance should be in the ending point. Okay. So we already have plus 250. And now we find minus 250 from
Minus
this
250.
segment. So if you balance this, it would be 0.
0, sir.
So we find these 2 points again from here to here. Here you can see simple equations. If the line is 0 degree action in the SFD, next to the first degree. So here you can draw linearly. Okay. Oh, sorry. Okay, we can draw the linear line. Up to this is clear. How do you draw this SFD and BMD? This is,
Yes, sir.
This is we call
Yes, sir. Clear.
SFD, and this is we call BMD. So here you can see all the moments are positive moments. So now my question is like that. All of the student can draw this, right? So if I say what would be the bending situation or bending curve, it will be like this. So if the beam bends, it would be like this. So this is the bending moment curve. Do you remember that sign convention?
Yes, sir.
Yes, sir.
Positive.
So if all the moments are positive, it's like this. Now very interesting answer for you, that if the pen you hold in the mid of the classes, right? So can you take the pen again?
Yes, sir.
Okay.
Yes, sir.
So this is interesting if you understand, otherwise okay. You might feel very bored. So now you have a beam. Suppose, just for an example, you have a beam, right? So this beam, suppose you consider this is the beam, has a tendency to have all the moment as a positive moment, right? So did you take the pen?
Yes, sir.
So you apply the positive moment. How does it look like? Look like this, right?
Yes, sir.
Okay. So to resist this bending, right? In beam, in your practical life, you will find 2 layer. You have the rod in this upper layer and the bottom layer. In the drawing class, you might see, right?
Yes, sir.
Now, can you tell me that which rod will resist this positive bending? Upper layer rod or bottom layer rod?
Bottom.
Very good. So that means what? You know why do you place bottom layer rod, or where we put the bottom layer rod? That means what? Where we have the positive moment, right? So technically, in the position where we do not have the negative moment, okay, vice versa, you can also learn this situation. If we have if you have some beam which is having the negative moment, so this beam is having only the negative moment, just for an example, right? So which layer will you consider the rod then? To resist, you will consider the upper layer. Do you understand or not?
Yes, sir.
We'll consider the upper layer,
Yes, sir.
rod,
This time upper layer.
rod for the negative zone. Okay. So that's why you can say that in the beam where you find the moment is positive, that locations you put the bottom layer rod, and where you find the beam is having negative moment, that layer you put the rod in the top layer. Do you understand that?
Yes, sir.
Yes, sir.
So now if someone asks you that, okay, engineer, why do you put the rod like this? You put some rod here, you put some rod here, and you put some rod here. This is a typical beam situation, right? If it is a fixed support on the beam, if you have the fixed support. This is the practical situation, just to give you more interest on the bending moment diagram, that why do you need this? Okay, so to give you more attraction. So if you have the fixed support on this, so you know the beam diagram, beam movement diagram would be like this. Why does my, oh my goodness. Okay, ignore my bad drawing. Suppose this is the beam. Usually for the beam which is having the fixed support on the both end, the moment diagram is look like that. Do you understand? So this is the negative moment,
Yes,
this is
sir.
the negative moment, this is the positive moment.
Positive.
So that's why in typical beam, in the both side is fixed support, you'll find this kind of diagram, and upper layer on this negative zone you'll get the rod for this. And this negative moment will contributes, resist this rod, and this positive moment will be resisted by this bottom layer rod. Do you understand? So now if you look into the beam reinforcement detailing, you'll easily understand why they put more rods on the bottom layer in the mid portion of the beam. Why do they put more rods on the top layer in the end of the beam? Do you understand now?
Yes, sir. Interesting, sir.
Yes, if you understand. Otherwise, you will say, sir, time's up. Okay.
No, sir. This. Yes, sir.
Okay, then. Now the time is for question and answer. If you have any question, you can ask me. And next class, I will continue with the more lectures, more examples. What you can practice from this segment, this is very easy. Have a look. If you consider W instead of the load 100, right, you can see that the shear is W by 2. So if you consider W is 100, so here we find the shear is 50, right? Very simple. Simply the formula generated, here shear would be W by 2. So if the W is 10, here shear would be 5. Similar way, what is the maximum moment you find here? 250, right? You remember? But
Yes,
if
sir.
you consider W and L, you will get the formula WL by 4. So what is W? 100. What is L?
100.
10.
10.
What is
10 is
4?
10, sir.
So you can see that.
4 is 4.
250.
Okay?
250, sir.
250. Do you understand? So you practice with like that. So if you simply remember, if it is simply supported beam, maximum moment would be WL by 4. That's it. So whenever you will be in the real design courses, that time you don't have to draw this kind of diagram. So you will usually use this kind of shortcut technique. So hope you understand. So we'll try to practice more examples in upcoming classes. Okay? Any more question from your side?
No, sir.
No, sir.
Okay, if there is no questions, thank you very much. So please do revise. I'll upload the slides today. So please do revise, otherwise you'll forget. And this is the most important thing for your life if you want to live like a civil engineer. Thank you very much. If there is no question.